Okay, well, great. It's nice to see everyone. It's my pleasure to welcome you to the Monday seminar. We've been doing this for a while now, and it's an absolute pleasure on a Monday afternoon in Europe, Monday morning in the US, and other places. We have been very lucky because of people like Andrea, who's organized the talk for us today. And she's going to talk about, you can see her title here, pore pressure cycles. The formal part of the introduction is always done by email, and if you're not part of the email list, I encourage you to join. We have a few more weeks. I've been doing this for a long time now, and at the end of this semester, sometime in May or early June, I'm going to end. And at that point, encourage maybe someone else to take over and lead us in a slightly different direction or a completely different direction, but we'll see. Um, our normal mode of operation is to ask people to mute themselves, but to encourage them to join in, to just unmute and ask out loud if you've got some point of clarification, question along the way. Helps um, Andrea probably realize that she's not just talking to her screen and there are people there. And then we have at the end an extended period for questions and discussion, and I will repeatedly invite you to join into that discussion. So with nothing further, I will thank you, Andrea, and turn things over to you.
Okay, thank you very much. Thank you all for being here. I'm excited to present and discuss with you some modeling work I've done over the past years that could help us understand to what extent could pore pressure cycles drive slow slip events. So I'll start with something that is well known, that is that slow slip events have been detected in many subduction zones worldwide. So this is a map of different regions where slow slip events have been observed geodetically. And as you can see, this phenomenon is pretty widespread. And one of the challenges of slow sleep is to try to explain why are they so ubiquitous. So among these different regions, slow sleep events share many characteristics. For example, they have slow and aseismic velocities that range from a few orders of magnitude above the plate rate to a few orders of magnitude below seismic speeds. They are recurrent, and in many cases, they occur periodically with periods ranging from months to years. They have long durations, also covering a broad range. And one of the interesting aspects of slow sleep is their dimension. They could be tens of kilometers wide and extend for hundreds of kilometers along strike. But despite these long durations and big dimensions, these events, the cumulative displacements of these events is relatively small, ranging from millimeters to tens of centimeters. And because of these big dimension and small displacement, the stress drops of slow sleep events are relatively low compared to earthquakes, and they range from 10 to hundreds of kilopascals. So we know that slow sleep events along subduction zones can occur at both deep and shallow depths. So this plot shows a schematic of a subduction zone, and these events occur in the transition from the locked to the creeping regions, both up deep and down deep. And they are also associated with different types of signals, such as very low frequency earthquakes, low frequency earthquakes, and tectonic tremors, which are enduring low frequency signals. But in this talk, I will focus on geodetically detected slow slip events. So one of the main characteristics of the environment of SSEs is that it's characterized by hyperfluid pressures. So these are evidenced by several observations, including high BPBS ratios in regions where slow sleep events occur, the presence of a low velocity layer, tidal cycles modulating tremor activity, and also high conductivity anomalies in regions of slow sleep. So these all have been interpreted as evidence of both that there's a lot of fluids around and there's also there's a lot of pore fluid pressure. So this is a schematic of a subduction zone where slow sleep events occur. So this is in Cascadia. And this evidence of high pore fluid pressure has been interpreted as an indication that the plate interface at the source depths of slow sleep events is sealed, or in other words, that the permeability is really low at this boundary, and that would effectively trap the fluids beneath and would cause a higher pore, cause a buildup of overpressure. But we will see later that this boundary is not as sealed as it was once thought, but in any case, it is pore fluid pressures are really high in many regions. So where do the fluids come from? At least for deep SSEs that occur in warm subduction zones, we know that metamorphic dehydration reactions coincide with the depth range of these events. For colder subduction zones, it's less clear the correlation with metamorphic dehydration reactions, and it is possible that some up-deep migration could occur. And for shallow SSEs, we have dehydration reaction of clay minerals, but they do not really coincide with the location of SSEs in several shallow environments. So it is believed that water trapped in subducting sediments could play a bigger role. So laboratory experiments also characterize the properties of the materials at the source depths of slow sleep events. So these experiments are often carried out in the framework of rate and state friction, which most of you will be familiar with. So these laboratory-derived friction laws relate the friction coefficient with two main variables, the sleep velocity and the state variable that characterizes the asperity contacts, and also the constitutive parameters A and B that vary depending on the temperature, pressure, and level of pore fluid pressure. So we know that after a step change in velocity, the friction coefficient increases, which we call a direct effect, and then it evolves over a distance d sub c. So after this evolution, the friction coefficient could either increase, which we call velocity strengthening, and A minus B is positive, or it could decrease, which we call velocity weakening. And this behavior is prone to more unstable sliding, such as earthquakes. So there's like a lot of experiments that have been done. So this is just a compilation of A minus B measurements on different materials, so granite, gabbro, quartz, and these were very important to inform our understanding of the mechanics of slow sleep. So for example, early understanding of slow sleep considered that A over B at the source depths of slow sleep was transitioning from velocity weakening to velocity strengthening, both up deep and down deep. So following up on the mechanisms, there have been several mechanisms, a lot that have been proposed to explain SSEs. So I'm just going to mention briefly some of them, but I'm not going to go into too much detail. So one of maybe the most cited ones is this work by Liu and Rice, 2007, where they uncovered like that changes, transitional friction behavior combined with hyperfluid pressure conditions, which are both consistent with what we observed from lab experiments and geophysical observations, that those two conditions provide a very favorable environment for slow sleep generation. There's also other mechanisms that take into account the fact that the friction properties of the fold may change from velocity weakening to strengthening with an increase in sleep velocity. And this mechanism has proved to widen the parameter space where slow sleep occurs. Delatency strengthening refers to the porosity expansion of materials that undergo shear deformation, and that affects how fluid, the level of pore fluid pressure, and may quench unstable ruptures and stabilize the fold. Other models consider changes in fold geometry and frictional heterogeneities, both of which are consistent with geophysical observations that the environment where slow sleep events occur is very heterogeneous, both in terms of relief, fold roughness, and also in terms of the materials that compose these rocks. And at last, the frictional viscous deformation has been explored in the context of deep slow sleep events because there's a lot of indication from the geological record that deformation is viscous at these depths, frictional and viscous. So there's a new understanding of slow sleep event mechanics that has been motivated by recent observations that indicate that pore fluid pressures actually vary over time during slow sleep events. And I want to take some time to explain some really amazing observations that were made along the shallow Hikurangi margin, along the east coast of the North Island. Here, inversion of focal earthquakes mechanisms were used to investigate pore fluid pressure changes. So the focal mechanisms were constrained for earthquakes within the subducting Pacific slab. And what they found is that, well, they calculated what is called the relative stress ratio, which relates the difference between the principal and intermediate compressive stresses. And this parameter is negatively correlated with pore fluid pressure. So they use it as a proxy to understand pore pressure fluctuations. And what they discovered was really interesting. So this is a schematic diagram, not the actual results, but what they found is that this relative stress ratio cyclically varied during slow sleep events. And this variation in this ratio was interpreted as changes in pore fluid pressure, in that pore fluid would steadily increase before slow sleep events and suddenly drop at the onset of sleep, and this would occur cyclically over the slow sleep cycle. There's other evidence also from geophysical observations that indicate pore fluid pressure changes in time following slow sleep cycles, and that is based on changes in BPBS ratio obtained through receiver function analysis in Cascadia and Hikurangi. So in this case, I'm referring to the deep Hikurangi subduction zone where we have long-term slow sleep events. There's also temporal variations in anisotropic seismic velocity that have been interpreted as fluids that feel microcracks and that affect the anisotropic seismic velocity. There's also temporal changes during SSEs in Japan and changes in seismicity rates and also seismic attenuation associated with SSEs in Japan, all of which have been interpreted as changes in pore fluid pressure at this location of slow sleep events. It's interesting to note here that the inferred pore pressure changes in these observations are in the order of 10 to 10 megapascal, whereas the stress drops of SSEs are between 10 to 300 kilopascals. So this is not intuitive at first sight, and it hasn't been explained like by a model. So there's also geological observations that indicate pore pressure fluctuations in exhumed subduction zones. So one of the most commented one is the presence of crack seal textures in exhumed subduction zones. So these crack seal textures just signal episodes of crack formation where pore fluid pressure exceeds lithostatic load and a crack forms. The crack is then filled by fluids, and these fluids precipitate minerals which close the crack. And this process repeats cyclically, indicating pulses of pore pressure change. So there's also evidence of cross-cutting relations between veins that indicate rotation of the stress field that may be due to transient changes in pore pressure at near lithostatic. That means very high pore fluid pressures that exceeds locally the lithostatic load. And there's also other evidence from subduction metamorphism records and lithium isotope diffusion data that point to the same direction. There's a caveat here in this observation, and that is that, for example, in the case of the veins with crack seal textures, we really don't know that these textures extend for from the tens to hundreds of kilometers where we see slow sleep events. So these pore pressure fluctuations during SSEs are often interpreted in the context of this fault valve model. So this model refers to cycles of opening and sealing of permeable pathways within the megathrust shear zone. So this can be explained by this diagram, where this is motivated by the observations along the shallow Hikurangi margin. So we have a subducting oceanic slab where before SSCs, we find a sealed plate interface, a very low permeability barrier. This barrier traps the fluids within the subducting slab. And as the pore fluid pressure builds up, it eventually reaches values close to lithostatic, which starts fracturing the rock. And these fractures eventually induce sleep along the shear zone. And the sleep enhances these fracture networks and allows permeability to decrease enough for fluids to migrate from this lower plate to, from this lower plate to this upper plate. So then these cycles of pore fluid pressure would be driven then by the accumulation or entrapment of fluids and the migration of fluids, which would modulate fault sleep. So based on these observations, there have been many numerical models that have explored the interplay between fluid flow and fault sleep. I'm just mentioning a few here. For example, there's recent models that have coupled permeability evolution, fluid flow, and fault sleep. Other models focus on the porosity evolution, like the expansion or contraction of pores and how that affects fluid flow. And yet other models consider viscous deformation and porosity evolution in relation to dehydration reactions and how that could possibly influence the recurrence intervals of SSCs. But I want to focus now on, there's also other signals that have been associated with SSCs, such as with fluid flow, such as rapid tremor migrations and also LFEs. Explained by this fault valving model. But I want to focus now on this fault valve instability. So here we see very interesting diagram that explains first the classical instability that shows the interplay of different variables, the sleep, the state variable, and the strength or stress of the fault. So this interplay would control the sleep behavior. The fault valve instability includes more complex interplays because it has to account for the evolution of permeability, which of course is affected by the sleep and the fracture connectivity, and that in turn affects the fluid flow and the pore fluid pressure. So this type of fault valve instability has been explored in 2D models by Osawa 2024, but it hasn't been explored in 3D. So because it's been a 1 to 2D comparison, the models that I've shown, like these, 1 to 2D model approaches, the comparison to observations has been limited. So I want to start now by introducing our modeling approach. So we're also motivated by these observations, but we consider a much simpler model in which we account for a one-way coupling between pore pressure and sleep. So we only account for pore pressure in the sense that it affects the effective normal stress on the fold, which is given by the lithostatic load minus the pore fluid pressure. So if we go back to the diagram that I just showed, our model basically is dominated still by the classical instability. We account for the interplay between these variables, but we artificially impose pore pressure changes in the model and see how it affects the strength of the fault. But we do not account for how the sleep, for example, could enhance the permeability and affect the fluid flow, which is a much complex process. But because of the simplicity of this model approach, we can study how this process, at least in a simplified way, is behaving in a 3D planar fault. So we conduct models within rate and state friction framework. These types of models have different ingredients. One of them is, as I mentioned, laboratory-derived friction laws. We account for the aging law in the evolution of the state variable. We also assume a continuum fault model and a fully dynamic relation between stress and sleep. The fault slip in this model is controlled by this equation where we're assuming an equilibrium between the shear stress and the frictional strength, and the pore fluid pressures are just affecting the frictional strength. So the model geometry and the simulation. So we consider a planar fault in a 3D infinite medium, and we use the simulation code bicycle modified for deep sleep. So we're assuming a thrust fault. And these types of models are governed by different nucleation sizes, which have different dependencies with respect to the B over A, B and A parameters. So to model the pore pressure perturbations, we assume that fluids diffuse along the fault plane. So first, we assume that fluids are injected from the walls of a circular cylinder that you can see here that is perpendicular to the fault plane, and that they diffuse radially along the fault following this diffusion equation. So basically the fluids we don't account for fault normal migration of fluids only along the fault, and this is consistent with observations in that fault parallel permeability is larger than fault normal. So we expect that the fluids will be moving along the fault and not normal to the fault preferentially. So the diffusion equation is solved analytically via the numerical inversion of the Laplace transform. So this is given by this equation here, where Q sub 0 is the injection rate. We assume there's a constant injection rate, and R sub 0 is the radius of the circular cylinder where the fluids are injected, and this has a radius of 1 kilometer. And this kappa is the permeability to dynamic viscosity ratio. This term here relates gives the dimensionless pore pressure evolution, which we solve using this Steffest method. So we impose pore pressure changes periodically on the fault, and this pore pressure evolution is given by this equation that is exemplified in this diagram. So we assume fluids are injected at the center of the fault over a time t ing, which we call the injection time. We prescribe a maximum amplitude of the pore pressure perturbation with respect to the background effective stress, and fluids diffuse with a diffusivity D and diffuse away with a larger diffusivity dB. So we assume that fluid pressure increases and then decreases, and these occur periodically. So the characteristics of the perturbation are controlled by the maximum pore pressure, the hydraulic diffusivity, and also the injection time. We consider that all of these parameters are free parameters, and that we explore just the parameter space by varying these three parameters and also the perturbation period. So the size of the perturbation is given by this diffusion length scale, that is the square root of the diffusivity times the injection time. And we have also the maximum pore pressure. So this plot here shows the evolution of pore pressure along depth for a given parameters. So we consider two end-member cases. One is that first we assume that the fault has velocity strengthening properties, and second we consider a fault that has velocity weakening patch that is surrounded by velocity strengthening region. So these observations are motivated by previous results for the case. I'll focus now on the case with velocity strengthening properties. We know that previous models have explored perturbations in stress on velocity strengthening faults, and they have found that they could lead to aseismic sleep. So I'm talking about Perfettinian and Puero, and also this has been explored in the context of induced seismicity by Dublanche 2019. So we know that if we apply perturbations on a strengthening faults, external stress perturbation, we can induce aseismic sleep. So this is basically exemplified in this diagram here. So if we increase the pore fluid pressure on the fault, we can induce this sleep that is shown here by these orange contours.
Andrea, it's
Yes.
Chris. Just to clarify a couple things that you said. So you don't in the model you don't include a normal stress effect on the state variable, the so-called like Linker and Dietrich term. You don't consider it.
I don't include it for the velocity strengthening case, but I did include it for the velocity
Ah,
weakening case.
okay. And then you said at one point that you didn't really include coupling between permeability and changes in fault properties, but it looks like you have something like that in there because the diffusivity changes. So,
Yes, yes, but the diffusivity is only affecting the rate of propagation of the flow, but it's not affecting the sleep. I'm not, it just affects how the fluids diffuse, and
oh,
that
I see.
affects the stress, the effective stress, but it doesn't influence, there's not a feedback with the sleep, which
Gotcha.
is the
Okay.
case of the fold valve
Okay.
instability.
Thank you. Thank you.
Um, So these are just to show some of the model parameters. We assume uniform friction properties with A minus B positive. And we consider, following Perfettinian and Puero, we consider nucleation size given by this parameter. So I'm going to show now an example of an induced aseismic sleep after pore pressure perturbations. So just to clarify, so in this model, we're considering that the fluids are injected over a period of 3 days and that hydraulic diffusivity is 25 meters squares per second. These are very high values, and I will go comment on that later in the talk. And the maximum amplitude of the perturbation is 1.5 megapascals, so this is half of the background stress. So these are the results of these perturbations. So we impose the perturbations every 2 years. And as you can see, the red lines indicate the pore pressure change, and the blue lines are the change in the sleep velocity. So these pore pressure perturbations periodically induce SSEs, and not, I mean, SSE-like behavior in that the velocity on the fold increases several orders of magnitude above the plate rate every time we impose the perturbation. And this behavior is quite regular. So these SSEs are basically the same event, just induced over and over again as we impose the same type of perturbation. So these are just to illustrate how the model behaves, the evolution of some of the field variables, where this black line indicates the the sleep velocity. So you see that the perturbation induces orders of magnitude change in the sleep velocity, which then in the period between perturbations drops way below the plate rate, which is in this case given by this line. And this occurs cyclically as we impose changes in the effective normal stress. It's interesting to note that after the first perturbation, the shear stress drops quite significantly, but the following perturbations do not cause such a large drop in the shear stress. So I'll go to the implications of that later in the talk. So this is an example of the evolution of the sleep rate during one of these induced SSEs. And this is a log scale. So red colors are above the plate rate and blue colors are below the plate rate. I'm not going to show all the lock-in. It is much locked than just 3 orders of magnitude below, but just mentioning it. So this is from 0. So this is counting the injection time. Sorry. So you can see that it takes a long time before we start unlocking the fold. So after 13, 14 days of injection, the fault is still locked in this region. And these contours represent the ratio between the pore pressure change and the background effective normal stress. So after 20 or so days, we start seeing sleep acceleration at the center of the fold. And this sleep acceleration transforms into a crack expansion event where the maximum sleep occurs at the front of the crack. And as we decrease pore fluid pressure, I'm going to go back again a little bit. So this is the perturbation is imposed for over 30 days or so. And then when it decreases, we see that the fold starts locking again at the center. So we calculated so these are, the stages of the sleep evolution. So after 20 days, we see a sleep acceleration, then it turns into a crack expansion. And at some point, it exceeds this 1% contour, which is 1% of the background stress. So this is the pore fluid pressure front. And after we remove the fluids, or the fluids start to diffuse away, it decreases at the center. So we calculated the stress change due to these SSEs, as is in the order of tens of kilopascals. And this is interesting because we imposed a perturbation in the order of 1.5 or exactly 1.5 megapascals, but the stress drop of the event is much lower. And this is comparable to what I mentioned earlier, that observations show that stress drops of SSEs are much lower than the estimated pore pressure change. So to isolate the effect of the perturbation size, we consider constant amplitude of the perturbation and the perturbation period. So we imposed perturbations of different sizes to calculate the properties of the induced SSEs. So I'm going to show the results here. So in this plot, I am showing the duration in log scale and the moment of induced SSEs. And this color bar indicates the dimensions of the size of the imposed perturbation normalized by the characteristic nucleation length. So we can see that SSEs of long durations and large magnitudes are induced by these type of perturbations. So it could range from months to years, and also magnitudes from 5.5 to even magnitude 8. And it's interesting to note that when we increase the size of this perturbation, we also increase the magnitude and the duration of the induced SSEs. So one of the interesting results in this plot is that the magnitude of the assumed hydraulic diffusivities, which are between 0.1 meters squares per second and 100 meters squares per second. So this is quite large, much larger by several orders of magnitude than we expect from measurements of this parameter. So we explore whether kind of to understand like what would be required for this model to reproduce the broad range of observations of slow sleep events. So we explored whether the model could capture the duration and moment of SSEs in different subduction zones. So I'm targeting here SSEs in Nankai, long-term SSEs in Nankai, deep Hikurangi SSEs, long-term SSEs in Guerrero, short-term SSEs in Cascadia, and short-term, sorry, I didn't define those terms, but short-term and long-term basically refer to how long duration of the event. So short duration events are usually short-term events, and they also have shorter recurrence times. And the idea is that we explore the model space by just varying the plate convergence rate. So we assume different plate convergence rate according to the subduction zone. And we assume that the period of the perturbation is the period of occurrence of the slow sleep event. So these are the results of our model. And as you can see, the model broadly captures the duration and magnitude of the target SSEs. I'm showing here by the colored lines, the areas where these events, durations and moments locate. And the main parameter that we vary in this case is this characteristic size of the perturbation. So as expected, these long duration, large magnitude events in Mexico would require larger perturbation sizes. So we also compare the area of the target SSEs. So as you can see, the results fit much less well in this case. So the model broadly captures the area of some of these events, especially the ones in Hikurangi, and also Mexico, but it doesn't capture the area of Cascadia SSEs, and we believe this is probably because these are very elongated events, and we consider a radial perturbation of pore pressure. We also compare the stress drops of some of the target SSEs with those of the model, and it broadly captures, at least is within the same order of magnitude, tens of kilopascals to 100 kilopascal. And it is interesting to note here that the imposed pore pressure changes for these different models is between 1.5 to 4.5 megapascals, but the stress drops of induced SSEs are between 10 to a couple of kilopascals, which is consistent with the inferences of observations. So if there's any questions, I'm going to move on to the second model, but I could take questions on these if you want some clarification, and I could drink water too.
Someone wants to join in? I think I'll personally wait, but yeah, if someone wants to join in, go ahead. Yeah, okay, so
Okay, I'll continue then. So in this second model, we consider mildly velocity weakening friction. So we consider a velocity weakening patch that is surrounded by velocity strengthening friction, and we consider a radius of the patch that has the same dimensions that we expect of SSEs of tens of kilometers. And I want to motivate like this model by going back to this earlier model by Liu and Rice. So we know that in their model, slow sleep events occur when there's a tuned length scale that is given by this W parameter that relates to a long, deep extension of the velocity weakening region that is under hyperfluid pressure conditions. This would be very low effective normal stresses. So in their model, when this parameter is close to the nucleation size, slow sleep events occur. And it is interesting that this early model could explain a wide range of observations, such as SSE duration, magnitude, stress drops. But the main criticism of this model is that it covers a very narrow parameter space, and it's not consistent with the widespread nature of slow sleep events. So that's why the motivation of this research is to try to understand whether pore pressure perturbations could increase the parameter space in this model. So this is an example of the reference model without pore pressure perturbations. So we can see that there's different sleep behaviors from continuous creep, SSEs, and earthquakes. And we're assuming here very mildly velocity weakening properties. And we are also considering changes in this effective fold stiffness ratio that, as I mentioned in the previous model from Liu and Rice, control where slow sleep events occur. So this first parameter exploration shows that SSEs arise only in a very few cases. And that if we went down here for more weakening properties, we would find more earthquake-like behavior and not many SSEs. So we follow the same approach as the previous case. So we impose periodic pore pressure changes at the center of the fault. So we assume the same equations. The only difference is that in this case, we use the aging law modified to account for changes in effective normal stress where alpha is 0.2. And as I said, the idea is to test whether we can increase the parameter range over which SSEs occur in velocity weakening faults when we account for these pore pressure perturbations. So to do that, we imposed different perturbations of different sizes on the reference simulation. So these are the reference cases that I just showed. And we changed the hydraulic diffusivity and the injection time to generate perturbations of different sizes, and we imposed them on these simulations as shown here in this diagram. After imposing these perturbations, we then classify the sleep behavior as you can see here. So there's repeating SSEs, non-repeating SSEs, SSEs, and earthquakes, and also only earthquakes. So just to highlight it again, so these repeating SSEs refer to the case where SSEs are induced at every perturbation and they have similar properties. So we basically induce the same event periodically after each perturbation. Non-repeating SSEs are just more complex SSEs in that they could have different properties, different duration, different maximum sleep rate, and it's not as regular the pattern of SSE occurrence. SSEs and earthquakes are both earthquakes and SSE sequences. And we also, in some cases, the perturbations are so high that the fault behaves very unstably and it generates earthquakes. So we do not impose perturbations in the earthquake regime because we were interested mostly in reproducing quasi-periodic SSEs, but we know that in this regime, these perturbations mostly lead to earthquakes and SSE sequences, but not periodic SSEs, which is what we were looking after. So I'm going to select some example cases of each of these sleep behaviors to exemplify the fault response. So in this figure, I'm showing the sleep rate evolution for each sleep behavior from repeating SSEs to SSEs and earthquake sequences. And these dashed line here indicate the time of each perturbation. And as you can see, repeating SSEs have a very regular behavior, whereas non-repeating SSEs are just different types of events that are induced at each perturbation. And for earthquakes, which we defined for velocities above 10 to the minus 2 meters per second, we see that they occur like in the same simulation after some of these imposed perturbations. But after an earthquake, you could have, again, slow sleep events. So these are just mixed sleep behaviors. So I'm going to focus now on repeating SSEs, which is mostly what we're interested in. So this is an example of the evolution of the full response during one of these events. This is the pore fluid pressure over time. And I note here that the pore pressure change that we imposed is really low. It's just 10% of the background effective normal stress. And we see that the evolution of the sleep rate indicates a migration of sleep fronts that nucleate and generate a crack that expands way beyond like the area that was perturbed by this pore pressure change. And this is an example of, again, the evolution of the sleep rate on the fold, similar to the previous movie that I showed. In this case, like we imposed a perturbation of 6 months. I know 0.1 years, sorry. So as in the previous case, we calculate the duration and magnitude of the repeating SSCs, as shown in this figure, and we also show it with respect to the normalized nucleation size. In this case, we're considering this nucleation size by Rice and Rina. And we can see that the induced events expand are kind of focused on the parameter space of long duration, large magnitude events. So we see that this whole space is pretty empty after the perturbations. And we also calculate the stress drop of the induced events, and they are again within the expected range for slow sleep event in the order of tens to 100 of kilopascals. We compared the results of SSE moment and duration for this velocity weakening case with the velocity strengthening one, and we can see that for velocity strengthening, similar hydraulic diffusivities and similar sizes of the perturbation lead to a much broader range of SSEs properties that could range from down to a month to larger magnitudes too. So from this, we speculate that, or kind of infer better, that velocity, these pore pressure perturbations are more effective mechanism for generating SSEs in velocity strengthening folds than in velocity weakening folds. So just to get an idea of what changed when we imposed the perturbation. So this is the original diagram where SSEs were only found in these two cases. But after imposing the pore pressure perturbation, we see a moderate, very modest increase in the parameter space where slow sleep events occur that I highlight here with these black squares. So imposing pore pressure perturbations in velocity weakening folds could increase the parameter space, but it doesn't make a very big difference, and it still wouldn't account for the widespread observations of slow sleep events. And in this case, in the velocity weakening case, these results are still constrained by this fold effective stiffness ratio because we need initially very stably sliding folds or folds that already experience slow sleep events so that they could turn into slow sleep event sleep behavior after we impose the perturbations. I want to comment now on one of the implications of our model, and I think one of the important implications is that to generate these detectable slow sleep events, because I'm talking about magnitude larger than 5, the hydraulic diffusivities that we had to assume were between 0.1 and 100 meters squares per second. So these are very large hydraulic diffusivities, very especially in comparison to what we have estimated. The largest estimated value is 0.024 meters squares per second. But since there are not many constraints of hydraulic diffusivity, we decided to translate this using a very simple assumption to permeability through this relation, where D is the hydraulic diffusivity. This is the fluid viscosity, effective compressibility, and porosity, which we assume was 5%. So we just assume average values for these parameters. And we found that the estimated permeabilities from this approach were between 10 to the minus 4 to 10 to the minus 10 meters squares. So these are very high permeabilities, but just noting that this is not the first or the only model that have suggested high permeabilities. There are other models that have accounted for, that have predicted large permeabilities to explain, for example, the occurrence of LFEs, or also that these high permeabilities would be explained by the occurrence of porosity waves in a viscously deforming medium. So there's definitely other um, models that have estimated such large permeabilities. So the question now is like, what could those permeability mean? What, or if there's evidence of that? And I found this very interesting plot on this paper by Munoz Montesino and Bear in GRL 2023. And they show here different estimates from different observations that I show here of the permeability at the source depths of slow slip events. So what they show here is that there's a background permeability that is in the order of 10 to the minus 10, 10 to the minus 18 meters squares per second for shallow SSE environments. And for deep SSE environments, we see even lower permeabilities of 10 to the minus 20, 10 to the minus 24. And that there's also other estimations that suggest that there's a transient increase in permeability that could shift these permeability estimates several orders of magnitude upwards, up to 8 orders of magnitude. So these, if you compare these estimates with the model results, we're still in the upper end of the estimated change in permeability. So what could cause these changes in permeability? It could be related to the fracture connectivity that is associated to the changes in pore fluid pressure, especially when they reach values close to lithostatic values. We know that there could be hydraulic fracturing that could change the permeability along the shear zone. And also, this is not accounted by my model, but we know that sleep also can enhance permeability and increase the connectivity of these fracture networks. However, there are still like many open questions relating to these mechanisms. For example, I talked about permeability increases, but we don't know exactly like how long could this permeability changes last? Are they comparable to the duration of slow slip events? Also, we don't know what controls the recurrence times of SSEs in these full valve model. So there's like a lot of hypotheses that these recurrence times of SSEs are related to the healing times of minerals and also the precipitation of minerals within fractures, but laboratory experiments are not conclusive regarding the time scale of these processes, and it's not clear that they could be comparable to the recurrence times of SSEs. As I mentioned earlier, this full valve instability has only been explored in 2D, but not in 3D, so we don't know if it would actually match observations of SSEs. And also an important variable to consider here is like the interplay with other factors such as frictional viscous deformation and full valving has not been explored. Also, what happens when we consider fault networks and rough faults. There have been some studies that I cite here that have worked towards that direction to explain that interplay. So to conclude, so we found that pore pressure changes in Brennan state faults could generate quasi-periodic SSEs, and the characteristics of these SSEs, the moment and magnitude, would change depending on the size of the perturbation and also the amplitude and period. We also found that to generate SSEs comparable to observations, the model requires very high hydraulic diffusivities that would correspond to permeabilities between 10 to the minus 14 to 10 to the minus 10 meters squares. And at least from our exploration of this one-way coupling, we found that this type of pore pressure perturbation seems to be more effective for velocity strengthening faults than for velocity weakening faults under pore pressure perturbations. So, and at last, I just want to highlight that there's still a lot to do. So we know that SSEs in continent occurs also in other settings, such as in continental fault systems, in landslides, also in the flanks of volcanoes. I show here an example of Mount Etna. And it's interesting to think whether these environments could give us insights into the mechanics of SSEs in subduction zones as well. So with that, I think thank you all for your attention, and I'm happy to take any questions.
Thank you very much, Andrea. Yeah, I'll invite people to unmute or join me in congratulating, thanking Andrea for a great talk. Give her a chance to catch her breath here for just a second, and then we can start a discussion. Yeah, okay. Lots of people sending you gestures. Yeah, so I'll just invite people to use the raise hand feature. It's the easiest way to put ourselves in some order and to start into questions and discussion. I will stop the recording to let people